Okay, good morning, children. Uh, Today we are going to start a new chapter, that is chemical kinetics. Now, this chapter deals with the rate of chemical. It deals with rate of chemical reaction. Now, there are different chemical reactions which take place, it occurs at a different rate. Suppose bursting of crackers. It is an example of a fast chemical reaction. Suppose rusting of iron. Rusting takes a month to take place. Okay, so rusting is a chemical reaction. It's very, very slow. And so we have fast reaction, we have very slow reaction. We also have reactions, which takes place at a moderate pace, at a moderate rate, not too fast or not too slow. They are called, moderate rate reaction. So fast reaction, very fast reaction, very slow reaction, moderate rate reaction. We can divide chemical reaction based on their rate into these three classes, into these three categories. Now, suppose we have a chemical reaction A plus B, arrow C plus D. So naturally A and B are the reactants, C and D are the products. Now, how do we express rate of a chemical reaction? How do we express rate of a chemical reaction? Now, if a vehicle, is traveling, suppose a vehicle is traveling, okay, and it also travels at a certain rate, and that rate, if we call it as speed, how do we find the speed? What we do is we see how much distance it goes in given period of time. So this distance by time, gives us the speed of the vehicle, give us the rate of travel of the vehicle. Now, in case of chemical reaction, how do we express the rate? Now, the rate of a chemical reaction, can be explained this way. But before that, suppose concentration of A, at the start of the reaction or before the reaction starts, suppose it is A naught, and suppose, so at T equal to 0, suppose the concentration of A is A naught, and say at T equal to T, that means after some period of time, the concentration of A definitely, it will be changing. Suppose it is A T. Now, which one is small in value? This one is small in value, because with the progress of reaction, amount of this will decrease. Concentration of this or the value of this will be less than this. So, what is the change change in concentration of A. So change in concentration of A, it is your third bracket A naught minus third bracket A T. The change in concentration of A. Now this change in concentration, suppose we are representing it by this. And suppose this change has taken place in time t. So we can say rate of this chemical reaction, we can say it to be change in concentration of A by time taken. Now, since okay, so now here we have done it, in terms of A. Similarly, we can do also in terms of B. We can also do, or we can express the rate in terms of C also, or we can also do in terms of D. So let me write down a general expression. So if this is a chemical reaction, we can express the rate of the reaction in this way. Suppose if I do it in terms of A, so it will be delta change in concentration of A, or if I do it in terms of B, it will be change in concentration of B. If I do in terms of C, it will be change in concentration of C. The change in concentration of T. Okay, now change we always measure final minus initial. Final minus initial is always we change. So here, though I have done A naught minus AT. Why I have done A naught minus AT? Because here A naught is greater than AT. That's why I have done like this. But in science we always calculate change in this way, final minus initial. So this change, this change delta A final minus initial, this value will be negative, because as reaction happens, reactants concentration will keep on decreasing. So this value is actually negative. Final concentration of A minus initial concentration of A will be negative. So this is a negative term. Now, since rate of a reaction, rate cannot be negative, so we have to do something so that this quantity becomes positive. So that's why we have to put a minus sign. In this, same with this also, because B is also the reactant, so here also we have to put a minus sign. We always will put a minus sign in front, for the reactants. And in case of product, it will be this only, because in case of product, final amount will be more than the initial amount. So rate of a chemical reaction we express in this way, that is change in concentration by time taken. Okay, now this term is also called your rate of disappearance of A. Similarly, this term will be called as rate of disappearance of B. This term will be called as rate of appearance of C, and similarly this one is known as rate of disappearance of D. But suppose if the coefficients of the reactants and products are not same, here it is same 1 1 1 1. If the coefficients are not same, then there is going to be something that has to be done. So first of all, let me take up a particular case where the coefficient is not same. Say this reaction, hydrogen plus iodine, it forms 2Hi. So here you see coefficient is 1, here the coefficient is 2. So here if I write like this here, for it will not be correct. R is equal to minus delta H2 by delta T is equal to minus delta I2 by delta T is equal to delta Hi by delta T. If I write like this, now it will not be correct. Why it will not be correct? Because here you see when 1 mole of A reacts, or when 1 mole of A disappears, then 1 mole of C is produced. Or we can say when 1 mole of B disappears, then 1 mole of C is produced. So rate of disappearance of reactants and rate of appearance of product is same thing. Because when 1 mole of this disappears, 1 mole of this is produced. But here you see it's not like this, because suppose when 1 mole of iodine disappears, 2 moles of HI is produced. So we can say that rate of appearance of HI is double. Rate of appearance of HI is double the rate of disappearance of H2, rate of disappearance of I2. That means this quantity is bigger than this one. This quantity is bigger than this one. They are not same. They are not same. These two are same. So rate is equal to this, not equal to this. Because this value is double of this value is double of this. So in order to make it equal, what we have to do here, we have to divide it by 2. So now it is correct. So whenever we have some coefficient, we have to divide by that coefficient. Okay, then we will get the expression for rate of reaction. So in general case, suppose we have a reaction AA plus BB arrow CC plus D. Suppose this reaction. So you see, we can write rate of reaction as minus 1 by A delta A by delta T. Third bracket term means concentration. Third bracket always means concentration. So it will be minus 1 by D delta B by delta T is equal to 1 by C delta C by delta T is equal to 1 by D this. So this will be the rate of rate expression we can write. Okay, so let us quickly take up a numerical on this. In exam, numericals are there on this. So suppose the numerical question is nitrogen and hydrogen combines to form ammonia as N2 gas plus H2 gas arrow 2NH3 gas. To balance it, here to 3. So nitrogen and hydrogen combines to form ammonia as this. If the rate of disappearance of hydrogen is 3.2 into 10 to the power minus 3 moles per liter per second. Rate of reaction, we'll have unit like this, moles per liter per second. Moles per liter is concentration by time. The rate of disappearance of hydrogen is this much moles per liter per second. So what we have to find calculate number A rate of disappearance of nitrogen, number B rate of reaction and rate of appearance of ammonia. Suppose this is a question, then how can we do this? So you see, according to this reaction, you can write this rate expression. Now, since the rate of disappearance of hydrogen is given, means we have this thing equal to this. So, if I put this value here, so it will be minus 1 by 3 into 3.2 into 10 to the power minus 3.